So in this little video, we're going to talk about how electrons in orbitals are related to the periodic table and how you write something called an electron configuration. All right, so previously we talked about the hydrogen atom, how it had energy levels at n equals 1 and n equals 2 and n equals 3 and so on, and how that every time you go up in this number n, you get a new type of orbital called an S type. Then you go to a S and a P type, and then a SPD type, and so on. And I've labeled the periodic table the S block, the D block, the P block, and the F block. All right, and so in the hydrogen atom, when you have 1, there's only the S type. All right, and so it's the lowest in energy, and so we're going to denote the 1s orbital energy by a box. And the reason we do that because there's an additional factor, and it's that the electron has a spin, and the spin has two orientations. It can be up or down. And so a hydrogen atom has one electron, so what we do is we put one arrow into the 1s orbital box that says, okay, hydrogen has this electron configuration, and we write this as 1s superscript 1. All right, so helium is the second element in the periodic table. It has a second electron. Its atomic number is 2. So in helium, the rule is you have to put 2 electrons in the same box. If you're going to do that, then they must have opposite spin. So if one is up, the other one must be down. And so this electron configuration is easily changed. You just put this as 1s2. You don't say squared, you say 1s2. Okay, well, now this box is filled up because there's only one s orbital type in each shell. So you have to go to the next shell, which is the n equals 2 shell. And n equals 2, there's an S type. And then there's also P-type orbitals, and there's 3 of them. So we're going to draw 3 boxes for the 3 different P orbitals. All right, and the rule is however many electrons you have, you keep adding them in the lowest boxes until you run out of electrons. Okay, and the other thing to keep in mind is if you put 1 in a box, the next one has to be the opposite spin. All right, so with lithium, which is element number 3, an electron goes in. And now the electron configuration is 1s2, 2s1. Now, if you'll remember, the hydrogen was 1s1. This is something and a 2s1. And as a matter of fact, there's a shortcut for electron configurations. And it's that all of the previously filled shell corresponds to one of the noble gases. Okay? And so when we fill the n equals 1 shell, you've got helium. And so we can write the 1s2 as helium. All right, so, and you keep adding electrons. All right, so whenever you get to the same number of electrons as you have in one of these elements, it always turns out that the last one you put in was a single electron into the largest n with a type S. All right, so for example, this was 1 electron in the 1s was the last electron put in. Last electron put in lithium was 1 electron in the 2s. Sodium, the last electron you're going to put in is into the 3s, last one in the 4s, last one in the 5s, last one in the 6s. So that's why these are called the S block. And all of these elements have 1 electron in the outer shell. These electrons are called valence electrons. So there's another notation for electrons, valence electrons. It's called the Lewis dot symbolism. So all of these elements have 1 electron in the valence shell, and so you denote them as the element symbol, whatever it is, and a single dot. All right, so let's go to the next group, which is group 2. All right, so the question becomes, do we put the extra electron in the n equal 2 p type, or do we pair up the s type? And the rule is, If they're not the same energy, you just put them in the lowest one. So we start pairing those two, and now we have for beryllium, we have 2s2. And so the second element in the p block is always an s. 2 electrons in the s orbital has 2 dots, 2 valence electrons. All right, and so now we're going to go across to element number 5. And so in element number 5, we're now in the p block. We start putting electrons into the p subshells. All right, and so we put 1 in. That'll be the one for boron. Notice we've been counting up. There's 5 electrons here. All right, so let's go ahead and modify the electron configuration for boron. By now we've reached 2 electrons in each of the s boxes, and now we're in the 2p shell, subshell. And this is the 2 different ways. This is the whole enchilada. This is the one with the noble gas shortcut. All right, but now we have 3 electrons in the n equals 2 shell, and so now whatever, in group 13, now some periodic tables is called 3A, so the ones with the A columns are called the representative elements. Those are the ones with valence electrons 1 through 8, not counting the transition metals. All right, so whatever this symbol is, 3 dots. Now we don't put the dots on the same side unless we kind of have to, and it doesn't matter where you put the 2 or 3 dots. Okay, you just put them on opposite sides of the Z. And all right, so that's boron's electron configuration. It's got 3 dots in the Lewis symbol. Next, all right, now since they are the same energy, you don't pair up the electrons yet. As a matter of fact, it's slightly better energy-wise for the total energy of the whole atom to have 2 electrons in the same subshell in 2 different boxes and with the same spin. So we have to draw this second one as the same way we drew the first one. Now, we could be pessimistic and always down, but people always put the first one up, and so that means you have to put the second one up. All right, so this is called 2p2 because there's 2 electrons in the shell. Now notice how there's less information here, because here it doesn't say where the 2 electrons are. Here, this says the 2 electrons have to be in 2 different p orbitals, and they have to have the same spin. Now these rules are for how you get the electron configuration for the lowest energy state of the atom. I mean, the atom can be in higher energy states. It just wouldn't have the electrons in these boxes in these ways. All right, so we'll continue on. All right, and so in this, I'm going to go ahead and write the orbital subshell names. All right, in the last, so we got carbon, and we have 4 valence electrons, and so I'm just going to go ahead and write the actual example of carbon with 4 dots, because it has 4 electrons in the n equals 2 shell. All right, so nitrogen is going to have 5, oxygen 6, fluorine 7, and the noble gas is 8. All right, and so noble gases, when you reach 8, so this is going to be the one for helium, so I'm just going to keep going. That was nitrogen here, that's 2p3. Oxygen, you have to start pairing them, and then that is going to be neon. All right, so let's go ahead and talk about neon a little bit. All right, so 2p6. All right, so neon, 1, 2, 3, 4. Now you have to start drawing 2 dots everywhere. And so the Lewis dot structure for neon is going to be 4 dots, 4 pairs of dots. And notice that we can only put 6 electrons into the 2p subshell, and that there is 6 elements in the p block. This is the one with the p1 configuration, p2, p3, p4, p5, p6. All right, so it turns out that when you fill the p subshell and get p6, that's when you get a noble gas. The atoms really have nice stable energy because the next one you have to fill up is much higher in energy. So the next one in the series is the 3s, and then the 3p, and you have to know this order, by the way. But the order in which you fill in the periodic table tells you which order they appear. So S block, filling the S block, second S block, the 2s, the 2p, the 3s, and I know it's 3s because it's in the S block. And then I actually fill the, whoops, I believe I've done my periodic table wrong. Yep, I have. So, excuse me while I fix that. Got my D block 2, because I knew the order was wrong when I started doing that. So, I'm going to leave this in because it's a useful sort of thing to understand, as nobody's perfect. And, like I said, you can use the periodic table to tell you what's right and what's wrong. So the 3s, and then followed by the 3p. All right, so I knew the 3s followed the 3p, and that's why I said, well, we can't be in the D's yet. All right, so after the 3p comes the 4s, and then the 3d. All right. Now, the D-type orbitals have 5 boxes. That means you can put a total of 10 electrons because you can put 2 in each box, one up and one down. And so it turns out that this is really tricky because the energy of the 3D is about the same as the 4s. All right, and so it turns out that for certain elements in the periodic table, it's actually more favorable to do what the book talks about, these exceptions where you have an S1D5 or an S1D10. So make sure you understand those 2 exceptions. But in general, for the neutral atoms, we fill the 4s first because it comes first in the periodic table. Then we start filling the Ds. This is the 3D block. And then we start filling in the 4p, which I don't have room on my screen for. All right, so the order in which the orbitals appear is the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. All right, and so the periodic table, which you will always have access to, kind of tells you, if you know which block is which, you know which elements start filling which subshells next. All right, well, that's it for electron configurations.